Our Milky Way is on a collision course with the nearby Andromeda Galaxy, a sprawling arrangement of several 100 billion stars. This cosmic collision will eventually bring both galaxies into a shared dance, merging them in dramatic and transformative ways. Andromeda, central to the early understanding that the universe doesn't revolve around us, has been a focal point in galactic studies for over a century. Its discovery helped prove that the Milky Way wasn't the only galaxy, which revolutionized our understanding of the cosmos. For much of history, the Milky Way was seen only as a faint, continuous band of light across the night sky. Early technology couldn't resolve it into individual stars, which led to many misconceptions about its nature. This view shifted in the early 1600s when Galileo Galilei used his telescope to reveal that the Milky Way was a vast collection of stars, planets, and other celestial bodies, rather than a single unified structure. His work disproved the idea that the Milky Way was the center of the universe, unveiling it as a sprawling galaxy of countless stars. In 1750, British astronomer Thomas Wright proposed that the Milky Way was a flattened layer of stars that included our solar system. This theory was advanced given the technology of his time. In the 1920s, Edwin Hubble utilized the Hooker telescope at Mount Wilson Observatory to show that distant nebulae, including Andromeda, were actually separate galaxies with billions of stars. This discovery transformed our understanding of the universe. Andromeda, also known as M31, has been observed since at least the 10th century when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud, one of the few galaxies visible from Earth's surface without a telescope. In 1612, Simon Marius gave the first telescopic description of Andromeda, laying the groundwork for future astronomers. Charles Messier officially catalogued it as M31 in 1764. A major leap in understanding Andromeda came in 1864 when English astronomer William Huggins analyzed its spectrum, identifying it as different from ordinary gaseous nebulae, a crucial observation. Andromeda is massive, estimated to have a mass between 1 and 2 trillion times that of our Sun, and is thought to be around 10 billion years old, suggesting a complex history formed by the merging of smaller protogalaxies. Previously, astronomers thought Andromeda was significantly larger than the Milky Way. However, recent research indicates that the masses of the two galaxies are much closer than once believed. While Andromeda spans about 220,000 light-years across, the Milky Way measures between 100,000 and 175,000 light-years, highlighting its vast size. One of Andromeda's intriguing features is its active galactic nucleus, powered by a supermassive black hole with a mass of 110 to 230 million times that of our Sun. Observations from advanced telescopes like the Hubble Space Telescope showed 2 points of concentration in Andromeda, with a brighter one slightly off-center, indicating intense gravitational interactions and the presence of a massive black hole. Andromeda also hosts a rich array of globular clusters, with around 460 clusters each containing thousands or even millions of stars. This abundance is evidence of Andromeda's history of galactic cannibalism, where smaller galaxies were absorbed, adding to its stellar population and diversity. Recent observations suggest that Andromeda may transition from a typical spiral galaxy to a ring galaxy, a relatively rare type characterized by circular ring-like structures of young, bright stars. Ring galaxies can form through cosmic collisions or when a smaller galaxy passes through the center of a larger one, making them unique among galactic formations. The impending collision between the Milky Way and Andromeda is an epic event anticipated to begin about 4 billion years from now and will unfold over the subsequent 2 billion years. This grand encounter will ultimately result in the formation of a new supergalaxy, nicknamed Milkomeda by astronomers and enthusiasts. The merging process will be marked by intense gravitational interactions and tidal forces, significantly affecting both galaxies. As the Milky Way and Andromeda approach one another, their immense gravitational forces will begin to distort each other's shapes. This gravitational interplay will pull stars, gas, and dust from each galaxy, creating elongated tidal tails and sparking complex gravitational interactions. The overlap and merging of the two galaxies will be anything but smooth. It will be characterized by turbulent and dynamic transformations as their structures are gradually torn apart and reformed. One of the most striking consequences of this collision will be the formation of new star clusters. As the galaxies collide, gas clouds within them will interact and compress, leading to bursts of star formation. These stellar nurseries will be regions where intense gravitational forces compact the gas to the point of collapse, forming new stars. These newly formed stars will often be grouped into clusters, enriching the new supergalaxy with fresh stellar populations. Simultaneously, the gravitational upheaval will alter the orbits of existing stars. Stars that once orbited stably around the center of the Milky Way or Andromeda may be thrown into new, more elliptical paths or potentially flung out of the merging system entirely. Some stars might find themselves ejected into intergalactic space, becoming rogue stars no longer bound to any galaxy. This redistribution of stellar material will contribute to the formation of new cosmic structures, and may result in a complex web of star streams and clusters that blend the remnants of both galaxies while forming new ones. In addition to forming stars and clusters, the merging process will also create vast, complex structures within the new galaxy. The gas, dust, and stellar debris from both galaxies will mix and settle into new configurations, forming large regions of star formation, warped arms, and potentially new galactic features that are a hybrid of the original structures of the Milky Way and Andromeda. These features will evolve over time, shaped by the dynamics of the merged galaxy. The supermassive black holes at the centers of the Milky Way and Andromeda will also play a crucial role in the merger. As the galaxies coalesce, their central black holes will eventually merge, forming an even larger supermassive black hole at the heart of Milkomeda. This merged black hole will be a powerful energy source, significantly impacting the surrounding stellar environment and contributing to the new galaxy's active and evolving structure. In the end, the merger between the Milky Way and Andromeda will result in a profoundly altered cosmic landscape. The new supergalaxy, Milkomeda, will be a vast entity composed of the blended material from both predecessor galaxies. It will feature a rich tapestry of new star clusters, altered stellar orbits, and restructured galactic features. This process of cosmic evolution, driven by the collision and merger, will shape the future of the local group of galaxies and offer an intriguing glimpse into the long-term dynamics of galactic interactions. The merger will bring profound changes to our night sky and, potentially, the environment on Earth. Influencing biodiversity, living spaces, and the environment, this cosmic cycle will unfold long after humankind is gone. Our Sun will eventually become a red giant, making our solar system inhospitable in around 5 billion years. The merger of Andromeda and the Milky Way raises questions about the future of our solar system and the potential formation of new cosmic structures. These vast cosmic interactions may create a new galactic environment, possibly including habitable zones for future forms of life, though likely quite different from what we know today. The Milkomeda Galaxy, formed by the Milky Way-Andromeda merger, will stand as a testament to the dynamic, ever-evolving nature of the universe. This galactic collision, anticipated to occur in about 4 billion years, will mark the end of a gravitational dance that began billions of years ago as these two massive galaxies gradually approached each other across the vastness of space. As the merger progresses, astronomers expect significant transformations in the galaxy's spiral structures. Currently, the Milky Way and Andromeda exhibit distinctive spiral arms that radiate from their central bulges, shaped by the rotation of stars and gas around a core. However, as they draw closer, gravitational forces will warp these spirals, stretching their arms into long tidal tails composed of stars, gas, and dust pulled from their original orbits, creating a mesmerizing, chaotic display across the cosmic landscape. This collision will also ignite intense bursts of star formation within the newly forming supergalaxy. The mingling of gas clouds from both galaxies will cause them to compress and heat up, leading to the birth of massive, luminous star clusters. These clusters will serve as nurseries for young stars, whose energetic radiation will light up the surrounding cosmic dust and gas, producing new stellar populations. The merging process will impact not only the galaxy's appearance but also their internal dynamics. Gravitational interactions among stars and gas clouds will shuffle their orbits and velocities, with some stars ejected into more eccentric orbits and others flung out entirely to become rogue stars in intergalactic space. Meanwhile, the supermassive black holes at the centers of the Milky Way and Andromeda will play a crucial role in shaping the future of the combined galaxy. These colossal entities, each millions of times more massive than our Sun, will spiral toward one another due to gravitational waves emitted as they draw closer. The final stages of this black hole merger will be cataclysmic, releasing immense energy as gravitational waves and radiation. The merger will ultimately create a single, even more massive supermassive black hole at the center of the new galaxy, surrounded by an accretion disk of gas and dust. This powerful central engine could influence the galaxy's evolution by regulating star formation and impacting the motion of gas and dust within the galactic core, potentially triggering quasar-like phenomena as material falls into the black hole and radiates intense energy across the electromagnetic spectrum. On a larger scale, the merger of the Milky Way and Andromeda will contribute to the ongoing evolution of cosmic structure in the universe. Galactic mergers and interactions are crucial in the hierarchical model of galaxy formation, where smaller structures combine to create larger, more complex systems over cosmic time. Studying galactic collisions like the one between the Milky Way and Andromeda provides astronomers with insights into the mechanisms driving galaxy formation and evolution. Observing how stars, gas, and black holes interact during such events allows scientists to test theoretical models of galaxy mergers and deepen their understanding of the processes involved. This merger will also have implications for the distribution of dark matter within the newly formed supergalaxy. Dark matter, an elusive form of matter that makes up a large portion of the universe's mass, plays an essential role in shaping galaxy structure and their gravitational interactions. During the merger, the dark matter halos surrounding the Milky Way and Andromeda will interact and combine, affecting the overall distribution of dark matter in the new galaxy. Observing these effects will provide valuable clues about the nature and properties of dark matter, helping astronomers unravel one of the greatest mysteries in modern cosmology. The Milky Way-Andromeda merger will also offer a unique opportunity to study the formation of galaxy clusters and superclusters, vast cosmic structures composed of multiple galaxies bound by gravity. These colossal structures, the largest known in the universe, provide insights into the large-scale distribution of matter and the evolution of cosmic web-like structures. As the Milky Way and Andromeda merge, they will bring their respective satellite galaxies into the process. These smaller galaxies orbiting their larger counterparts will be gravitationally drawn into the merger, potentially merging with a new supergalaxy or being torn apart and incorporated into its extended halo of stars and gas. The fate of these satellite galaxies will depend on their orbits and speeds relative to the merging Milky Way-Andromeda system. Some may remain relatively intact as dwarf galaxies within the new supergalaxy, while others may be disrupted and eventually absorbed into the larger structure. This merger will also impact the cosmic environment surrounding our solar system. While the collision itself will not directly threaten Earth, gravitational disturbances and increased cosmic rays from the merging galaxies could subtly affect our planet's climate and radiation exposure over geological timescales. Additionally, the formation of the new Andromeda Galaxy will create a fundamentally different night sky for any future inhabitants of the Milky Way. The merger will alter the positions and distributions of stars, star clusters, and nebulae, potentially creating new constellations and celestial landmarks that could shape the cultural and navigational aspects of any civilization that arises in the distant future. In summary, the collision and merger between the Milky Way and Andromeda represent a cosmic spectacle on an incomprehensible scale, a process that will transform both galaxies, creating a new supergalaxy that blends the material and characteristics of its progenitors into a unified cosmic entity. From the reshaping of spiral arms and the birth of new star clusters to the fusion of supermassive black holes and the redistribution of dark matter, every aspect of the merger will leave an indelible mark on the future evolution of the local group of galaxies. Studying this event provides astronomers with a unique opportunity to witness the profound power of gravitational interactions in shaping the universe. It serves as a reminder of the dynamic, ever-changing nature of cosmic evolution, where galaxies collide, merge, and ultimately result in new structures and phenomena that continue to inspire awe and curiosity in the exploration of the universe.